Okay, so welcome to the Frosty Drew live YouTube experience. Tonight's another clear night like last week, so we're going to have live views from the telescope. In fact, you're seeing the star Pollux, whereas last week we started with the star Betelgeuse. Once again, my name is Derek. Tonight we have Jessica here as moderator for the chat channel.
Hello.
And hopefully we get some good questions. We had a couple last week. It'll be a pretty similar format to what we did last week. We'll try to do some different objects and go. All right. So like last week, my laptop can't do all the presentation things that we're doing and run the telescope. So I have to use my desktop, which is over here. And once we maybe find a better studio solution for doing these YouTube lives, you won't have to look at the side of the presenter's face. But nonetheless, that's what we're going to do tonight. So the star Pollux is paired with the star Castor. They're in the springtime sky, and they are ahead of Leo, but they're behind Orion and a little bit further towards the zenith or the top of the sky. I'll move this out of the way, and you'll be able to see kind of the constellation behind there. So last week we started over here in Orion, and this week we're going to start here in Gemini. And then also we're going to do a little bit over here in Cancer, which is the next one before Leo, constellation-wise. And these, as you'll note, are probably pretty similar to the Zodiac. And that's because these are the constellations that are on the Zodiac, which is really the constellations that are on the plane of the solar system, which allows the sun to travel through them. So, okay. Let's see. Where are we going? All right, yeah, over here. So, oh, I turned that off by accident. There we go. All right, so the first object we're going to look at is an open cluster, which is a group of stars that are kind of, they're all closely associated with each other. They likely formed together from the same star forming region, and they're still, grouped together, and they usually number in the dozens to hundreds. Where there's a similar or kind of a similar object that's a globular cluster, which typically the stars number tens to hundreds of thousands, and they're formed differently, and they're structured much differently. But we might look at one of those later tonight. Depends on how things work out with the clouds, because we are expecting some weird overcast conditions tonight, which is why we're not doing nebulous tonight. All right, let's take a picture and see what we get. And just like last week, where'd my button go? All right. And this is M67, which is a Messier object, which is in the constellation of Cancer. All right. And we landed on it, so let's go over here.
So Derek, if you were looking just up in the night sky, where about would this be? Would it be kind of like directly overhead? Would it be towards the north? Where is it?
Right now, it's kind of due south and about halfway up the sky. And a good way to find this one is if you draw a line between Regulus, which is the foot star in Leo, and this bright star over here in Canis Minor, which is Proxion, about halfway across that line, and then you go up to kind of the root of Cancer, you'll pass through M67, which is this open cluster that we're looking at. And one more time, taking a picture. Um, this is the picture we got. So we're going to try again. Telescope is still moving. And those star streaks, as we talked about last week, happen because the telescope's moving.
It looks like a crazy meteor shower.
Yes, that would. If that's a meteor shower that we are ever participating in, that is awesome. Let's see if we get a better one here. There's a larger open cluster in Cancer, and that's up here, and that's also known as the Beehive cluster. It's too broad of a field of view for my particular telescope, so we don't look at it, or at least I don't look at it with this telescope. But this open cluster is much smaller and a little bit takes up less space in the sky, so we can image it with this telescope. So you can kind of see like this just field of stars. It kind of has, some structure around it, and towards the middle, it looks like maybe the density of the stars is going up a little bit, and that region as we call it is an open cluster because the stars have a lot of space between them, and there's not a lot of gas there that's remnant from the star creation. And what ends up happening is the stars all form, and as their stellar winds liven up and become the dominant force in that area, it starts to push the gas out, and eventually all of the stars collectively push the majority of the gas out. And then throughout gravitational interactions, some of the stars get ejected, sometimes in pairs, sometimes single, sometimes in groups, and that's how these objects kind of evolve over the years. So
I've heard of globular clusters too. So what's the difference between, like that you said, it's an open cluster?
Yep.
What's the difference between an open cluster and a globular cluster, or is there a difference?
So there is a difference. The open clusters are typically within the Milky Way, and they have many or a couple orders of magnitude less stars. And when we say orders of magnitude, we mean 10 times. So an order of magnitude from 1 to 10 that's one order of magnitude. From 10 to 100 is another order of magnitude. So globular clusters have dozens to hundreds of stars, where globulars have tens of thousands to hundreds of thousands, and some of the largest ones potentially millions of stars.
Wow.
And I think I mentioned it earlier in the evening, or earlier in the discussion when I opened. We might be able to look at a globular later. There's a few that come up behind Leo that are pretty fun to pretty good sized globular clusters. So let's see. Yep. And from here, so I'm also fighting some trees in my yard where we can't go too far here to the east because we'll run into trees. But I think last week we tried over here. There is, I lose it every time. Sorry, you're watching me like scroll around. Oh, sorry, it's way down here. So yeah, we're gonna have to wait for that. Anyway, all right. So, yep. Let's see what this is. So the other thing that's neat about this open cluster is right next to it is a smaller open cluster. There's actually 3 of them here. There's another small one up here, and then another small one down here. So within the same field of view in a telescope, you kind of can see 2 of them side by side. And these aren't as prominent as there's a pair of open clusters in Perseus that's called the Perseus double cluster that's much brighter. But we'll go over here and take a picture so you can kind of see the difference between these 2 just real quick. All right, so when this image finishes, you'll see them change. Unfortunately, I don't have it set up right now to be able to do a side by side, but nonetheless. Yeah. And the other thing to note, globular clusters are typically orbiting. They're in the halo of the Milky Way, whereas open clusters are within the Milky Way. There are a couple of exceptions to that. There's a few globular clusters towards the core of the Milky Way, and those are thought to be captured from an interaction with another galaxy, where the Milky Way and another galaxy have merged, and that merging caused those globular clusters to be basically swept within the Milky Way galaxy. And we see those in the summer in the constellation Sagittarius. So you can see this open cluster is much less dense, and has, it looks like just the stars are spread out much farther, which is probably an indication that it's an older or open cluster, or it just didn't have as many stars form in it to begin with. So there's that. Okay. So I apologize. I was hoping Leo would be above the trees at 7:30, but it is not.
Thank you, Jessica.
So. Hey.
Looks like
Derek.
Appearance by Scott.
Yeah, I finally got in. I'm late as usual. That's the story of my life. A day late and a dollar short, right?
Yep. So I do have a few stock images of a couple things that I wanted to show you guys in Leo later tonight. But we can talk about them here and then try to do a live view of them later tonight. The first one I want to show you is an animation of about 2 hours of images taken over 2 different nights of 2 of the galaxies that are in Leo. These are known as M66 and M65. The one on the right is M65, the one on the left is M66. You'll notice a couple of different things in this sequence of images, and I'll pause it on one of the interesting ones here in a second, and I'm hoping this will show up in the Google Teams translated through to YouTube, but there's this streak that runs through the image, and I'll zoom in a little bit. And what I find interesting about this is you can tell that the satellite, or whatever this is, space debris is tumbling, because you have these bright marks along the trail. And if we go and this is something I plan on doing, and I didn't get a chance to do it before this, but we can go back and figure out what the tumbling rate of that object is if we figure out what that object is using a couple of different databases that we might be able to figure out which object it is, which will give us an altitude and a speed. So we might be able to figure out what their tumbling rate based on those bright spots. So that would be interesting if we ran that experiment by next time. The other thing in this series of images is kind of like last time. There's it's not in both nights worth of data, but there's an asteroid here going right there. So they're taking images along the ecliptic here. You run into a lot of asteroids because you're looking basically out of the solar system along the plane of the solar system, which is where the asteroid belt is. So you end up capturing a lot of those.
That's really cool.
I never really looked for them before, so this is kind of fascinating to me, even after doing this for a number of years, finding these in data that you're just not looking for it in. If it's coming up, all of these like speckles that are moving upwards are actually artifacts from the camera. The sensor has noise on it, and that noise walks up the image sensor in each successive image. So.
I like that the noise pattern you have over the spiral galaxy actually makes it look like it's spinning. which is absolutely ridiculous, but it is still cool to see.
Yeah. So, all right. And then if anybody was curious, after taking that 2 hours worth of data and stacking it, you get an image like that. So all the noise gets smoothed out, and then that's really the point of taking all those images and integrating them. You can take the best pieces from each image, basically pixel by pixel, and then build a composite image that represents the data of the image versus the noise. I mean, this image still has noise in it. You need a lot more data, or a lot more images to really push the noise floor really far down. But for something as bright as these two galaxies, this is 2 hours of data is sufficient. So
that really is a fabulous image, Derek.
But you can see here in M65, it has a pretty good spiral structure. It's kind of edge on, but you can see this dust lane that runs through here. This star that is basically right here on the dust lane is a foreground star in the Milky Way, as is this one on the edge of that galaxy. And these galaxies, I looked it up earlier this week. As far as distance, I'll look it up if anybody's curious. And then you can see this one over here. It's kind of got a disturbed spiral structure, and it is that way because it interacted with another galaxy. Potentially, the third galaxy in this collection, which is it's out of the frame that is presented here because, again, of the field of view of the telescope, but I do have an example of that image here. Yeah. So this is that third galaxy is called the Hamburger Galaxy, and this is granted a rough processing, but I was just going for pulling out the data to see what was there, and I like to explain why this one's called the Hamburger Galaxy. Because you can see that the gas halo around the galaxy kind of makes the top bun and the bottom bun, and then the dust lane running right through this edge-on galaxy makes the patty, and then it's just kind of fun. But you can see that this dust lane is not straight; it kind of tapers. So that tapering is indications that this galaxy has also interacted with another galaxy. Potentially M66, and we're seeing the results of that interaction through the disruption of the dust lanes in that galaxy. So, all right.
So all galaxies from like the side angle, would they all look different, or would they all kind of look similar to that one?
So that's a good question. They look similar but different. So this one, the gas halo is pretty uniform. If we go to another example of an edge-on galaxy called Needle Galaxy, which is in a constellation behind Leo, Como Berenices. Thank you. I pronounce it so infrequently that I stumble on it. This one is also an edge-on spiral galaxy, and you can see that the gas halo is much closer to the galaxy itself, but you can see the central bulge where the center part of the galaxy is kind of bulging out a little further than the arms. And that might be because this galaxy is undisturbed. It might be a fundamentally larger galaxy, so the scaling just works out differently. Again, I'm not 100% sure. And this one is part of the Virgo supercluster that we've been talking about now that it's galaxy season, and Como Berenices is above Virgo, but behind Leo. So that triangle between this constellation Virgo and Leo kind of forms the triangle that the majority of these galaxies.
Welcome to take a look if you like.
What do you mean by galaxy season?
So this Virgo supercluster comes around during the spring, and there's probably a couple of hundred objects, galaxies in this cluster that are of this size in angular diameter in the sky. The angular diameter of this object is about a quarter of the moon. So if you think about the width of the crescent moon when it's a quarter illuminated, that's how much of the sky this is taking up. Even though we don't see this naked eye, it's because it's so dim and because of the distance, not enough light reaches our eye without a telescope to be able to resolve this object. But it is still quite large in our sky compared to the pinpoint of a star. Yeah. So, all right. Let's see. What else did I have? So, one of the things, that asteroid that I showed you in M60 or near M66. Let's see. This is a website that's run by NASA, and you can go type in, the coordinates, the center coordinates of where you were taking an image. And I found this since last week. So if anybody remembers, I was talking about how we could potentially identify these. So I figured out how to do that. And you go in, you type in the center coordinates of your image, how much of a search area you want, and it returns back to you all of the objects within those search parameters. So as you can see, there's a lot more than one. Some of them are, too dim to see, even with the telescope. And the probable candidate for the one that we were just looking at, you kind of have to use another astronomy software that will plot that asteroid onto the planetarium software, and then you can see if it lines up with what was in your images. I don't know yet of a better way to do it, but refining that process. If anybody is interested, we'll keep talking about that. So it's just amazing to me how many asteroids are out there in such a small field of view. Never really thought about it. I was like, oh yeah, asteroids, they're spread out. There's not that many of them, but in reality, there are a lot of them, and they're there all the time. It's kind of crazy. All right. Wanted to talk about another tool that we use in astronomy for helping us predict the weather or the sky conditions. And this is the Frosty Drew Clear Sky Chart. And it was kind of interesting tonight. You've got this gray line around the scene, which is why I kind of am avoiding nebula tonight, because this usually means that dim things like nebula are they're not going to come through. The atmosphere it's either got too much moisture in it or other conditions. As you can see, there's a warning down here for possible smoke, which again, last year kind of got in the way quite a bit. If anybody remembers, there was all the big wildfires out west. These wildfires are down in the south right now. So this is a cloud plume that comes out, or smoke plume, really, and can get in the way of astronomy. So, all right. Let's see. What else can we talk about?
Scott, do you have something on the telescope there?
Dear God, do I? Yes, I do. I have.
There's a quick question that I wanted to talk about. I just noticed Nate is asking if M65 and M66 are viewable with a telescope. They're actually viewable in binoculars. They are quite bright. They're pretty close and bright, and they are visible in even 80 10 by 50 binoculars. An 8-inch Dobsonian does a really nice job on these two galaxies, and an 8-inch Dobsonian will actually show you all three components. I'll do a quick thing over here and show you kind of how close together those three are and where to find them. So you've got the back two stars here in Leo, and then you have this star down here, and it kind of makes a 20-degree turn. And then those three are about halfway down between those two as a group. So, and the second circle on the three circles there is the field of view for, I'm sorry, the outer circle is the field of view for 10 by 50 binoculars. So, if anybody was curious. All right.
I think Scott did have something in the telescope there at the observatory.
Live views.
Live views. Let's see what he's got.
Okay.
All right.
Thank you. So right now, we have the Orion Nebula in our telescope at the observatory. I'm going to share the control software with you real quick. All right, here we go. Can you guys see that?
It's loading.
Yeah.
So this here is running currently in, I don't know if you can quite see it. I'll put my red light on it. But this is the telescope right here. There's the next image. And what we're looking at here is it's called Messier 42, the Orion Nebula. And we're looking at a little bit larger than just the Orion Nebula right now. We're actually looking at the entire sword of the constellation Orion. The center star in the sword is the Orion Nebula, and it is naked eye visible. It's one of two naked eye visible star-forming nebulae in the northern hemisphere. Tonight in our telescope, it's very clear on site. So we have several visitors here. We have a lot of telescopes set up. The wind hasn't picked up yet to the point that we expected it to, though I do feel it's starting to pick up. And in this telescope, we wanted to make sure that we had a good view of the sky to present live. Now, let's talk a little bit about this object. What we're looking at here is a star-forming nebula. This is a star-forming nursery. That's there. Someone just bonked the telescope. And a star-forming nursery is, to put it plainly, where stars are being born. They're being formed. And star formation requires two very specific things. It requires mass and it requires gravity. So when we look at this cloud here, we're looking at a cloud of hydrogen gas, and that's the mass component. So something had to disturb this gas cloud, whether it be a supernova remnant, whether it be the untimely demise of stars that are forming inside this nebula, or would it be potentially another molecular cloud, another hydrogen cloud passing through. All of these things, they disrupt all of the gas and cause it to clump together. And that forms little dents in space-time, which is the fabric of space, and those dents are gravity. So once you have a little bit of gravity that forms, it starts drawing in all of that hydrogen around it. Now, gravity plus mass equals heat, and as temperatures rise in the core of those little gravity wells, eventually reach the temperatures required to fuse hydrogen to helium, and the energy output is dramatic. But gravity pulls it back in and you get a balance, and that is a new star. And that's what's happening inside here right now. About 700 stars have already formed inside this nebula, but there's enough mass to form about 2,000 stars before all of that gas gets blown away. Now, when you're looking here, you can see a series of different colors as well. One of these different colors that you can see is clearly all of this red. It's kind of almost like a magenta. And that's a product of the very bright region in the center here. Now, this is where all star formation is occurring. And a series of about 4 stars have already moved out of the cloud itself, and they're becoming visible and exposed. And those are called the trapezium stars. And those stars are casting a substantial amount of ultraviolet radiation into the gas cloud. And that ultraviolet radiation strikes these hydrogen atoms and blasts off one of their electrons, effectively ionizing the hydrogen atoms. So now you have hydrogen ions and free-flowing electrons. They want to reconnect. And eventually these hydrogen ions will reconnect with an electron, not the same electron, but an electron in the area. And when that happens, the atom gets excited and it glows, and it puts off that red glow. But when you look around the very outer edge here, you got a lot of blues in here. And these blues is from the intense blue starlight from the higher mass stars in the cluster, notably the trapezium stars. And all that blue starlight is reflecting off the gas cloud. But then if you look over in this region here, you have these dark wisps. You also have some dark wisps here across this reflection nebula. And these darker regions are what we call a dark nebula. And that's where you have parts of this star-forming nebula that are closer to us than all the stars that are forming inside of the nebula, all the ionization of hydrogen, all of that starlight being cast. And the side that we see isn't interacting with any of that, so it just looks dark from our point of view. And when you factor in all of these variables, that here are actually the stars that are forming, here's the envelope of this gas cloud, and this is regions of it that are closer to us than star forming itself, we actually can get a three-dimensional point of view of this object. Now, when you're looking below this, we have the NGC 1977 reflection nebula with star cluster. And initially, we thought that that star cluster may have been involved with this a bit. This could have been part of the gas cloud that this cluster of stars formed out of. But now we realize that it's not. It's just another molecular cloud passing through this small cluster of stars. And their starlight is reflecting off the cluster. And they're close enough, and there's enough ultraviolet light coming off, that there is a very slight red in here, because there's a little bit of ionization that's occurring. Now, the Orion Nebula is 1,400 light years distant from us. And that makes it very close to us on the galactic scale, but on the human scale, an easy way to think about that is that the view we're getting tonight live in the telescope is actually 1,400 years in the past. And if you want to see what it looks like tonight, you'd have to wait 1,400 years for the light to get here. So I'm going to turn the session back over to Derek, and I'm going to move to a different object. And then when Derek is done, we'll show you an open star cluster.
That was pretty cool looking. Derek, your mic is off.
I was just saying, if you have the field of view for the beehive, that would be cool. Because mine's too narrow for that.
I'll see if I can get that. I was going to go for 44 because I have the filter in, so I might be able to get the white dwarf in there.
We started with
46.
Yeah, that would be cool to see the comparison between 44 in my scope and your scope. All right.
Control paddle. Yeah. And then this here, this is a telescope here. We have the camera right over here. And then this is the tube. And this is the mount that it's sitting on right here. And then in the background is the observatory. I don't know if you can quite see it through here. That light that you see right over here, that's the observatory. That's me.
Do you have the dome open tonight?
We don't, because we're worried about the wind picking up too much and causing issues in regards to dust and everything in the observatory getting kicked up into the optics. Also, with 50-mile-an-hour gust threat, that's way more tolerance than the dome and the telescope can handle. And we don't want to damage our equipment before we take it out.
Very true. Well, here we have both Derek and Scott looking.
Yeah, I don't know, like drawing a blank. Never good.
So my telescope's going to go over the meridian right now. I was hoping we wouldn't quite be there yet, but we are. So we're going to let it swing all the way around here.
I was seeing if I could find a globular in the field of view that I can get to, but
I don't think M3 is probably not up yet, right?
Well, if it is, it's still too far down in the trees. for me.
You guys are welcome to look at my screen, though, as I do it. Please. This was the last object that we had in view. That's the Orion Nebula. And now we're going to try for an object called Messier 46. And we'll see if this pops up. And if it comes up, we'll go back to the live broadcast real fast and show everybody. So it happens with the telescope that I'm using tonight. I'm using a refractor telescope that's on what we call a German equatorial mount. And the German equatorial mount has got a very weird orientation. It kind of looks at planet Earth the way you should. You know, you're standing on a globe looking at what would appear to be a dome of stars over top of you. So looking at this with the alignment of this telescope towards the North Star, then you actually get an accurate view of the sky as it would apply to standing on a globe. But it gets a little tricky when it comes to actually doing data collection and star formation, or I'm sorry, doing your data collection, because what happens is you want the telescope dropping below the counterweights. So when that happens, you got to spin everything all around to get to the other side to look at it. Now, I have an image here, so I'll show this real quick. And the first image is a little streaked out. I might have bonked the telescope. I apologize. But what we have here, this is an object called Messier 46, and this is an open star cluster. Now, there we go. That's better. Now, we actually have a couple in our view right here, because this is another one over here. This is Messier 47. But Messier 46 is actually this cluster right here. And this is a good object to show at the moment, because Messier 46, or an open star cluster, is the second stage of star formation or stellar formation as we see it in the galaxy today. And the first stage of that stellar revolution is the star-forming nebula stage. We call it the H2 region stage, which is what we just looked at with the Orion Nebula. So in about upwards of 50 million years, this is what all the stars in the Orion Nebula are going to look like. The gas is going to be gone, and what you're going to see is a series of stars that are all clumped together, and they're being held together by their own gravity. Now, they're all sibling stars. They all formed from the same molecular cloud. And these stars, the gravity is a loose gravitational equilibrium. It's almost like a family. You know, they'll start together, and then as you get older, you start resisting each other, and then you leave. That's kind of like what's happening here. You have all of these stars, they're together, the gravity's holding them together, but as they start to get a little bit older, this cluster is exposed to things in the galaxy, things like interaction with molecular clouds, interactions with supernova remnants, interactions with the death of the high mass stars in the cluster, all of which almost cause a vibration amongst that gravitational balance. And on the very edge, stars start to detach. Stars typically detach with the stars near them, and this is where we get our binary and multiple star systems from. But occasionally a star will detach alone, and that's what happened with the sun. Now, this open star cluster has a really great little, you can call it Easter egg maybe, a nice little bonus in it. And it's not actually in it, it's near it. And it's this little spot right here that looks kind of out of place. What you're looking at here is the formation of a white dwarf star. Now, when you think about not high mass stars, 97% of all stars in the galaxy are not high mass. These stars don't end as supernovae, kind of like the sun. The sun's not going to be a supernova. Instead, what they do is they collapse down to a point where they can't get all of their electrons any closer, and then they blast off all of their outer layers of the star, the gas cloud, exposing the core of the star. Now, the core of the star is the white dwarf. It's no longer fusing. It's dead. And that outer layers of the star, the radiation zones, the convection zones, the photosphere, the chromosphere, the corona, all of that gets blasted off as this cloud of gas that keeps expanding. But in the early stages, about 10,000 years after the initial detach of the outer layers of the star, that white dwarf, that core of the star, is so hot that enough ultraviolet light is being cast into that gas cloud, and it's ionizing the oxygen atoms in that gas cloud. And it's the same principle as hydrogen ionization we were talking about earlier, where you blast off an electron and they have an oxygen ion and free-flowing electrons. So they do want to reconnect, and they will reconnect with each other. Different, though, each oxygen ion will not likely connect with the same electron it lost, but it will reconnect with an electron. And when that happens, it glows a little green, almost cyan. It's like right on the green-blue boundary on the spectrum, or the visible spectrum. And we can see that for about 10,000 years. And that's what's happening right here. But that's kind of strange. If you think about it, why would you think that we're looking at stellar demise of a low-mass star amongst a series of young newborn stars? That doesn't make any sense. And the answer to this is actually really quite simple. The star, and so this cluster here is it's a little under, I think, about 5,000 light years distant. So this object here, this white dwarf, is about 2,200 light years distant. So it's in between us and the open star cluster, and we just see it along the same line of sight. It makes them appear like they're together. And this is in the constellation Canis Major, which is one of Orion's hunting dogs. And Canis Major has the Perseus arm of the Milky Way. We commonly refer to it as the winter Milky Way, passes right through it. And this sits right along that galactic plane where all open star clusters reside, because new star formation happens on the galactic plane. Old stars that are no longer forming, and the very oldest stars in the galaxy, all reside in the halo region, which is off the galactic plane. Now, Derek, do you got something, or you want me to move to something else?
I was attempting to take a picture of Castor and see if that looked like anything.
You want to share?
Yeah, I'll share. I've just got some weird clouds here right now, so.
Oh, yeah, you keep them over there. Don't send them here.
All right, let's go back over here to, where's the share button? Yep. One of these buttons. Sorry. There we go. So this is we started the presentation with Pollux, which is the companion to Castor in the constellation Gemini, and they are known as the twins because they are two very bright stars that are quite close together in the night sky.
Oh, hey, Allie, how you doing?
And they are, the namesake for the second series of NASA missions that preceded the Apollo missions. Or Gemini is where that comes from. So I was hoping that we might be able to see the companion to Castor, but I'm not sure if we're going to see it in that glare. So maybe not the easiest thing to do in photographic astrophotography. But sometimes people ask what causes these spikes, and that's actually a side effect of the structure of the telescope. On the front end of the telescope, there is a cross that holds a mirror to reflect the light off of so the light hits the primary mirror at the back of the telescope, and it goes forward until it hits the secondary mirror, which is held by that cross, or it's sometimes called a spider, and then it goes back down to, in this case, a camera. If we were looking visually, it would be an eyepiece. And the telescope that I'm using is a Ritchie Creighton design, which uses two mirrors instead of lenses, which is what the telescope that Scott has is a refractor, uses lenses. Okay, so let's see. Like I said, we've got some weird clouds here. So we're kind of restricted to just bright stars until that clears off. There's another open cluster.
So, Derek, where is your telescope housed?
So I have a small shed in my backyard that the roof comes off of, and it's kind of a homebrew observatory. It's called a roll-off roof, and they're pretty common for amateur astronomers, hobbyists, and it became this necessary when setting up the equipment started approaching an hour. So building that about 6 years ago, now I can go outside, roll the roof off, turn everything on, and take the lens caps off, and we're ready to go in about 10 minutes instead of an hour, which has been very nice when you're trying to actually use your telescope instead of just set it up and tear it down all the time. But
gives you a little bit more of an incentive to use it.
yes, and for a while, the one thing that it is kind of annoying is when you do need to take your telescope down to, say, take it to Frosty Drew, there's a penalty to coming home and setting it up. But these things, sometimes it's worth it. And as I said, I fight trees because I live in the woods, and I don't have quite the same skyline that horizon that Frosty Drew has, but we make it work. So I kind of set the camera off angle here to show, hopefully, the two different clusters here. I think we hit it. We're gonna ask the computer to tell us where we're looking, because this is the picture we got back. So we can see this open cluster here, and then this corner should be. Oh wait, we got to zoom out. This corner should be the other open cluster that's here. So, I mean, when you're looking at the sky, open clusters aren't super obvious. You kind of have to know to look for them, because it can just blend in. They just look like more stars. And they do, exist more kind of along the galactic plane, just because that's the material that we're looking through. You have more opportunity for these objects to form. Whereas if you're looking out of the galaxy, you're not looking through a whole lot of material. And that's, kind of in the direction of that Virgo supercluster. You're looking out of the galaxy. You're not looking through the galaxy. If you kind of think about like the visual lines, whereas if you're looking towards Orion, you're looking out of the galaxy, but you're looking through the galaxy, the outer parts of the galaxy instead of the top or the bottom of the galaxy. When I say the galaxy, I mean our galaxy, the Milky Way. All right. So we were close. Let's try that again.
Right, they showed up. I got 44 if you guys want to see it.
Yeah, take a look at this. Is if anybody's keeping track of what Messier objects we've shown tonight, this is M35. Yep. Let's go for you, Scott. Mine's just stuck downloading from the camera.
Scott, the one that you have, is that another Messier object?
It's hard to turn off my mic when I am switching to presentation. Sorry about that. Yes. So right now, can you guys see the cluster?
Yep.
Yes.
So this is Messier 44. And Derek and I were talking about this earlier. This is a Messier object. And Messier 44 is another open star cluster. The big difference with Messier 44 versus Messier 46 is the distance. Messier 44 is very close to us comparably, and it takes up a much larger area of the sky, which is why it looks so much bigger than the little speck that we saw earlier when we were looking at Messier 46. Now, Messier 44 is also a naked eye visible object if you have dark skies. Tonight here at Frosty Drew, our visitors are able to look up in the sky and see it naked eye. Though to the naked eye, it does not appear as a star cluster. It almost looks like a little cloud or a little like a blurry spot in the sky that's about the size of the moon. And it's the same story with this cluster. We're looking at a collection of stars that are young. They're sibling stars. They form from the same nebula. And they're slowly detaching from the cluster and turning into independent star systems. Now, I did decrease my exposure a little bit, or my ISO, because I felt like I wanted to try to get some color in these stars because they're really beautiful. And I'm getting a little red here and maybe a little bit of greens up here, which are more blues. It's a product of my filter. But I think my filter is interfering. This is what it looked like at the longer exposure, just captured just before I switched over. Now I'm going to turn the telescope over to some galaxies. So Derek, did you want to take over for a bit, or do you want to chill out while I'm on?
I will show I finally got a picture of what I was trying to show with these two open clusters. So I will.
You got it. So.
So we had a question from Tim Myers. He said, what is the tastiest, messier object that is also tough to see from Frosty Drew? He said he's asking about for the entire year.
What is the what object?
The tastiest?
Messier object.
The Crab Nebula.
Yes, I'll agree.
But I'm vegan, so that's no one heard that.
There you go, Tim. The Crab Nebula.
I'll second that. So the Crab Nebula is is M1. It's the first Messier object, and it's a supernova remnant that's only a little over 1,000 years old. And that supernova was actually recorded in semi-modern history. Like there are records of the supernova occurring, and even over the I'll say 20-25 years of modern photographic astronomy, we've actually, as a society, been able to show the growth of the Crab Nebula by taking pictures year over year. But it's at this stage, it's incredibly dim. 300 years ago, when Charles Messier and his other comet hunters that were building this list or compiling the list, the object was probably quite a bit brighter. So they were able to see it in their telescopes 300 years ago, where today it is much harder to see, even in the instruments that we have today that are comparably quite a bit larger. Sorry, a little detour, but that was a good one. I like that detour. So what I'm showing you here is kind of two open clusters that are relatively close together in the sky. I've only got in the lower corner there part of the larger open cluster, and then towards the upper left you can see the smaller and more distant open cluster. And these two, it's kind of a nice juxtaposition to show you kind of how they look in the sky if you're looking for them. So sometimes they are just small smudges, and then sometimes they're quite large, even larger than the one I've got here. M44, the one that Scott was showing us, is probably 4 times larger than, or maybe even 10 times larger than what we have shown here in the lower right corner. And by larger, I mean angular diameter in the sky, not necessarily in mass or star count. So, all right, that's what I've got. Did you land on something yet, Scott? So I actually have a picture.
I don't have it just yet. I'm about to move to it. I had a group of awesome visitors show up that wanted to see what we were doing, so I got kind of shanghaied there.
Okay. I'm going to quickly bring up a photo of the Crab Nebula from 2015. So this one's one of my early attempts at astrophotography, so but it works. Present. All right, so share that. All right, so this is the Crab Nebula, and it's, as you can see, it's just a dust cloud. It's the remnants of a supernova, the remnants of an explosion. And even in these long exposures that I took to get this data, it doesn't really show all of it. There's a little bit more to it, and I still can't figure out why it's the Crab Nebula. Like, I don't see that structure. Somebody did at some point and named it the Crab Nebula. But you know, that's, if you're curious what the Crab Nebula looks like in astrophotography, that's what it looks like. I've seen it once visually with the 16-inch scope at Frosty Drew, and it was even dimmer than what we've got here. So it's a hard one. It's a hard one to see, which is probably why Scott likes it.
At the moment, I'm actually doing a capture of the Crab Nebula.
Oh, cool.
So we'll see what it looks like once the data comes in. It might be a little streaky at first because I have something called backlash in the telescope. But I will start getting ready to share my screen so you guys can see it, whatever it looks like when it comes in. Okay, so this is a much lower resolution image than Derek's was of the Crab Nebula. And you can see it right in the center of the field. This object right here is the Crab Nebula. Now I'm going to increase my ISO setting in a minute once this next exposure is completed, and we'll be able to get a little more detail on it because I have my ISO turned down a little bit for the last object that we were looking at. But you can notice that there's a lot of colorful stars in this field as well. Now, the Crab Nebula is, I agree with Derek. I have no idea why they call it the Crab. Sometimes I wonder if NASA named it, because NASA is always thinking about food, and I feel like anything NASA names is named after food. So possibly they were, you know, hungry. But
they need to feed themselves better.
Well, they got like the club sandwich asteroid and saw this stuff. I mean, it's just crazy. But the next image should have a little more detail. But one thing that's really amazing about this supernova remnant is that there is a fantastic pulsar that exists at the center of this object. Now, a pulsar is a stellar remnant. It's a neutron star, and it's a product of a supernova. So supernovae only occur with high mass stars. There we go. That's better. Stars that have more than 10, really, it's like 8 to 10 times the mass of the sun. When these stars die, it's not about electrons getting too close together. It's about neutrons getting too close together. And when those cores blast off their outer layers, it doesn't just blast it off as a gas cloud around it. It explodes off those layers and pretty much destroys or ejects everything around it. And what happens in this case is usually that neutron star that remains behind is a bit of that neutron star that remains behind is quite small. I mean, we're talking about an object that's the size of Rhode Island with the mass of the sun. And it was spinning at one point. As it got smaller, more compact, this is conservation of angular momentum, or point of inertia is called. It's like a skater that spins really fast when they bring their arms in. It starts to spin really quick on its axis. And when that happens, you get a very large magnetic field that forms around it. And that magnetic field will terminate or kind of come back down right around the poles, and it energizes those poles significantly to the point where they start casting a lot of light out, like two beams coming off the north and the south pole. Now, the object is spinning so quickly that it has something called precession of axis. The same thing happens with Earth, where even though we spin quickly, we have a wobble. Kind of think of a top spinning, and it forms that wobble. But in this case, it's happening so quickly that you can see those beams of light. They move around like this. And if you're in line with them, they'll blip at you, and it looks like a pulse. We call them a pulsar. Inside the Crab Nebula is a pulsar. You have something, Derek?
Not yet.
Okay, so I'm going to increase my sensitivity. I'm going to go all the way up to 12,800, and we're going to see if we can get a little more detail on this object. Now, my focal length isn't quite as high as Derek's was, and that's why it looks so much smaller in my field. But there is a lot to see here. If you want to see images of the pulsar itself, which we have imaged it, not at Frosty Drew, but in science, you want to check out the NASA Chandra X-ray Observatory. They've done a significant amount of work with this pulsar. And one of Chandra's own data scientists, whose name is Kim Arcand, actually lives in Rhode Island, Dr. Kim Arcand, and she has worked with the computer science department at Brown University to develop a virtual reality environment where you can actually step into this supernova remnant and observe the pulsar from an insider's point of view in virtual reality. It's a pretty interesting concept, and I tried it and I got seasick, but I enjoyed it until I threw up. With a little more exposure, you definitely can see more of this, of the object here. And the filter I'm using is probably not helping too much because the types of gas that are visible here are not necessarily a product of pure ionization like you would see in the formation of a white dwarf or in a star-forming nebula. So I'm going to swing the telescope now over to two galaxies called Messier 81 and Messier 82, commonly referred to as Bode's group. And we'll see if I have to go over the meridian. If I do, then we're going to have to swing the laptop over. Yeah, it looks like we will. So I'm going to see what we can do about saving the laptop.
Set that up. I'm taking a picture of M95, which is a galaxy in Leo, and hopefully this works.
Over this way. Oh, not that though. Keep this on this side.
Okay. So it looks like things have cleared up a little bit for me because I'm starting to be able to resolve galaxies again. This one you can barely see. So you've got the star field here. And then this, if you notice, this star is a little bit fuzzy. And then if you look really close, there's a bar across it with two spirals that kind of go out and around like this. So that's a barred spiral galaxy in the constellation Leo. This one in particular is M95. That's pretty close to what you would see in a telescope.
You say it's very faint, but you can see the bar and you can see the top and bottom spiral.
I can totally see that bar. Yeah. That's fantastic.
So Leo has, I started writing them down the other night. I wrote down about 30 galaxies that I want to take pictures of. It's just, there's a plethora of galaxies in Leo, and then it gets denser towards Virgo, and then it tapers off again. But it's pretty crazy how many galaxies are in that Virgo supercluster. The Milky Way is part of the Virgo supercluster, and that's kind of, if you think about it, our city. Whereas, you know, the Milky Way is kind of a neighborhood in the city, if you wanted to put an analogy on it. So right next door to this is another spiral galaxy, M96, and we'll slide over to that one and see how they compare. Let's see here. I need the button to take a picture. And I'm taking 10-second images tonight, if anybody's curious. And for whatever reason, it's taking like 30 seconds to download from the telescope. Not sure what's up with that tonight. Normally it's about 9 seconds. So we have to wait a lot to download the image. There we go. Ah, streaks. Try again. And you can kind of see, if I show you the planetarium view there of how close together those two are. You know, they're basically this distance of the field of view that the telescope has. So can't quite fit them in the field of view of this one, but if you had a telescope, this telescope has a 1600 millimeter focal length. So if you had a typical 8-inch Newtonian and you were doing photography, it would be about twice the field of view. Okay, so this one you can tell it's got the bar, but the arms aren't as distinct as the M95 arms. So, and then from these two, if we go kind of in this direction, there's another grouping of galaxies here. The brightest one is M105, and that is kind of an elliptical galaxy, which is something that happens later in a galaxy's life, after it kind of just, the angular velocities are just kind of all randomized and it becomes a sphere or an ellipse shape. So let's see what that looks like. And that randomization happens through interactions with other galaxies. So we should see a couple of different galaxies in this next picture, since there's a few here. Oh, come on. Too fast on the button every time.
Got another meteor shower there.
Another meteor shower there, yep. That's what we'll tell everybody.
Like, we're all missing it. We should all be at Derek's house.
Yeah. This is the Leonids in April. Or March is they were.
Yeah, still in March. Yeah.
Still in March. Man. I've completely lost track of time in this last year. It's insane. Anyway. Yeah, there we go. Okay. So we can see this is the M105 galaxy. It just looks like a point of light, but it's not focused to a point of light like a star, because it does have that cloud of material around it, which is really all the other stars in that galaxy. And the point of light is the core of the galaxy, that just the density of stars is high enough to look like a star. And then you have this one here, which is an NGC object. I don't know the number off the top of my head. We'll look real quick after I slide this out of the way. And that one's kind of more of a, you see a different perspective on an elliptical again. So it kind of looks more elongated. And then this dim galaxy down here is another NGC, and it's a disrupted spiral, because it's probably been interacting with these two elliptical galaxies. So we'll zoom in here and kind of give you the similar field of view. So that's NGC 3371, and then this down here is NGC 3373. NGC is the new general catalog. It was put together in the 1900s, and then the M designations are Messier objects. Some of them are also NGC objects because the catalogs all overlap. But the M is Messier, and that was put together in the 1700s, as we kind of talked about earlier. Oh dear. And these are also just under Leo. about halfway between Regulus and the nebula back star. So if you're ever trying to find those with a telescope, and these are visible in a telescope similar to these three here, this is where the Leo triplet is. So, and then if you really want to challenge in Leo, you go up here towards the head, and there's four in a group that are kind of really hard to see with a telescope, but you can do it on a good dark night at Frosty Drew. So, take a quick image of those, and then see if Scott has landed back on M81 and M82. I can't image those from my house, so that's one of the things I always try to image when I get out to the observatory, because they are towards the North Star, too far for my tree line that I've got here.
It really amazes me on how many galaxies there are out there, like in any given shot that I've seen Scott take or other people too. It's like if you enlarge and you kind of keep looking deeper into the picture, it's like pretty wild.
The Hubble Deep Field that they keep adding to is they just picked a random spot in the sky and said, let's take a picture for a couple hours. And Hubble not having the whole atmosphere in the way thing, it has an advantage, but there's like a couple hundred galaxies you can spot easily. And then if you start looking at it, it's like, oh wait, that's a galaxy, that's also a galaxy, and it just keeps on going. So you can see these four here. You've got there's like an edge-on spiral, and then two very dim smudges that these probably won't show up in a telescope unless you're really, really lucky. This one's kind of interesting because it's got this like S shape because it's like been highly disrupted. And then this one up here is an elliptical. And then we'll look at them real quick with the planetarium just because it's a little bit easier to see what I was talking about there. So here, I'll do this so we can maybe see them. No, yeah, that's good enough. So kind of gives you an idea of what's there and what you can see with your telescope. Did you land on M82 yet, Scott?
I am. I'm going to share the screen. All right, so right here, we currently have that's what we call Bode's group or Bode's galaxies. What we're looking at is a series of galaxies with two rather bright galaxies in the field. And this is Messier 81 and Messier 82. So this is 81. And Messier 81 is a barred spiral galaxy that is almost face on to us. We're not looking directly at it. It is has about 30-degree tilt on its axis from our point of view. But even in this view, you can still see the two primary spiral arms that come off the galactic nucleus. Above it is M82, which is part of this grouping of galaxies. And M82 is very different. So M82 is considered a starburst galaxy, first of all. Secondly, we see it on edge, which means that when you look at this galaxy, we see the galactic plane and the spirals. This galaxy here is tilted almost 45 degrees from our point of view, so we only see the edge of it. Kind of how Derek was describing earlier with the Needle Galaxy and the Hamburger Galaxy. But because it's a starburst galaxy, we see a substantial amount of star formation happening in this galaxy. And it's because this galaxy had recently merged with another galaxy. And from that merger, a new galaxy had formed. But when that happens, all of the molecular hydrogen clouds, the nebulae, they start mixing with each other. And that mixing causes collapse in those nebulae, which is star formation. So you get a massive increase in the amount of stars that are forming in a galaxy, and we call that a starburst galaxy. And you can, though you're not getting a very good view of it here, you get a very nice, very large red region in here in this galaxy. And that red is ionization of molecular hydrogen. I mean, to be able to see that level of star formation on the galactic scale is impressive. There's other galaxies in the field here as well. You have a little galaxy sitting over here. And an image I captured just before I went live again, I had this slightly out of the frame, and there's another galaxy sitting right down here. And this is one of the closest galactic groups to the local group, which is what the Milky Way is part of. And this galactic grouping resides at 11.825 million light years distant. And that sounds far, and it is far. I mean, our view tonight of this is 11.825 million years in the past, because it takes that long for the light to reach us at the speed of light. But as far as the universe goes, this is literally right next door to the Milky Way galaxy and the local group. Close enough that these objects are just about binocular visible in the sky, and they reside towards the North Star in that region. They're generally between the North Star and the pointer stars in the Big Dipper is where we often find these.
So Scott or Derek, yeah, someone was asking, well, they're kind of talking about that they've never seen the Milky Way, and what is the best month, like April, May, June? When's the best time to come to the observatory to see the Milky Way galaxy?
So observing the Milky Way at Frosty Drew, there's definitely a season. And when you say viewing the Milky Way, I assume that you mean looking at the Milky Way's galactic nucleus and then all the spirals that we can see in between it, because that's that really bright view. The Milky Way is out all year long, but you don't always look in that direction. When you see pictures on the web, that's what you're looking at. So the best time to observe it at Frosty Drew is in April, but it's in the morning hours, about 3 o'clock in the morning. And the reason why that's the best time is it comes down to our location. So our best view of the sky is in the south. We do have a lot of light pollution from the local region around here. And at 3 o'clock in the morning, a lot of business lights and a lot of people's house lights and their garage lights are turned off. So you're at the lowest point of localized light pollution. But we also, it gets quite wet. The dew points rise in the spring, and we get a lot of that moisture in the air. But by about 3 o'clock in the morning, a lot of it is fallen to the ground and everything is wet. The sky is very clear. And additionally, to add to all that, the Milky Way is in a perfect position in the sky here at Frosty Drew to see. It is directly due south, which is our best sky to look at the Milky Way in. So that's why it's the best time of the year to see it here. You can see it similarly through May, but if you want to see it from a more accessible time frame, like after sunset, June and July are really great times at Frosty Drew to see it as well. And in July, you'll see it in the south like 10 o'clock at night, right when astronomical twilight ends. You got something, Derek?
I was going to show the M60, the supernova that was in M61 last year, compared to a follow-up image from this year.
Excellent.
To show people the difference. All right, so last year there was a supernova in the galaxy M61, which is in the constellation Virgo, and it's part of the Virgo supercluster. It happened late in, well, kind of midsummer, about June, was when it was first detected, maybe towards the end of May. I was able to take these pictures pretty much right after I got the camera, and you can see the difference between these two pictures. This one was taken this year, and this one was taken last year. So this picture was on June 14th of 2020, and this picture was on March 5th of 2021. And the spot to see a difference is if we look at this galaxy. Let's see if this scrolling thing is going to work. Sorry, doing this in a very cheesy way, but it works. You can see that, you know, you've got the galactic core on both images, and then you have this star in both images, which is a foreground star in the Milky Way. as is the one up here at the top of the arm and the one here. But in the image from last year, there's this extra point of light, which is a supernova in M61 that's shining just as bright as a star in the Milky Way, which, if you think about, is crazy, because all of this stuff that we see as clouds and gas that makes up a galaxy is millions of stars collectively shining to give us enough light to, resolve the galaxy. And then you've got this star having gone supernova, and this was a 1A supernova, so one of the brightest ones, and it outshines its entire galaxy. Not the collective shining of the galactic core, but it does outshine the entire galaxy. And it's a tremendous amount of energy that gets expelled during a supernova. Scott, was that your hand for jumping in, or just touching the laptop? Anyway,
that's me just talking to people. Sorry.
Oh, it's all good. And the cool thing about the Type 1A supernovas is they have a extremely predictable light curve. So we can measure that light curve and its intensity and know precise distances because of the relative luminosity that we see here and detect here, compared to the ideal or the known mathematical curve for that light. So it's a good tool for measuring distances. And you can actually see in this picture, I've gotten a little better at focusing, because the one on the right, the galaxy is not as well focused as the one on the left. So yay, improvements. But I thought that was a kind of a cool side-by-side to be able to show. So
it definitely is. I always think it's phenomenal when people catch pictures like this of where there was something there and now there's not.
And then this is probably the third supernova since I started doing amateur astronomy. M82, which Scott just showed, had a supernova. I think it was 2014, and that one was crazy because it was detected first by an astronomy class on the rooftop at some university. A freshman taking a class was looking at M82, and they were looking at their textbook, and hey, this is not in textbook, and they discovered a supernova, that was crazy. I don't know. It's always fun to talk about how things are discovered. But yeah.
Usually by accident, right?
Usually by accident, absolutely. Space is big, and only recently have we finally established surveys that can do the entire sky in a night or two. Meaning they just have a telescope that robotically just takes pictures of the sky, and then computer software to compare the images to see if there's any changes. And they've found tons of asteroids that way. They've found supernovas that way, novas, all kinds of transient events is what those types of surveys are looking for. So, all right. Let's see what else we can do.
Yeah, Scott, do you have something? Or I had something that kind of came up in the chat.
What came up in the chat?
Well, he's it says gaming with Aiden. He said that he's thinking of getting an 8-inch Dobsonian telescope so he could start viewing planets and deep sky objects. Do you think that's a good kind of telescope for that kind of focus?
I think that's a perfect telescope for that.
Yeah.
So an 8-inch Dobsonian is kind of the sweet spot across the board. It's enough aperture to look at tons of different objects: planets, the moon, the Messier catalog, NGC objects, comets. but it's also small enough where it's easy to move around and transport. So you're not killing yourself trying to move it around. And it's small enough where you don't have to do collimation or calibration adjustments on it every time you move it. So, and it's also relatively inexpensive. So I would say it is a fantastic object to start with.
Yes. I have an 8-inch Dobsonian, wouldn't trade it for the world. We have 2 8-inch Dobsonians at the observatory. They get used every Friday. And it's, as Scott said, it's a good all-around instrument. They're quite portable. They fit, on the back seat of most cars when you take the tube off the base. So it's a very, very good starting point.
Yeah, you can fit it in the back of a Honda Civic. So you can't go wrong with that, right?
What year does the Civic become wide enough to fit an 8-inch Dobsonian? That's the question.
Yeah, I've done it in the old 96, so maybe.
Just making a joke that the Civic seems to be getting bigger every year.
Oh, I know. It's no longer a small car, right? I saw a Civic the other day. I thought I saw a minivan. Yeah. So right now I'm swinging the telescope over to an object called Caldwell 49, more commonly known as the Rosette Nebula. So I am going to get it in place, and now I'm going to start firing away and see if we can score a view. All right, so capturing now. My exposure set, I'm running at 30 seconds to get a decent view. I felt like if I went any longer, I'd have a lot more detail, but it would take a lot longer for me to actually show you guys all that awesome. So I'm kind of finding a happy medium here at 30 seconds. Now, the Rosette Nebula is quite large, and it's not necessarily dim overall, but it's called surface brightness. You're looking at a bright object spread out over a large area, so it actually appears a bit dim. So I'm going to share this. The first image just came in, and this is the Rosette Nebula. You see it, Jess?
Not yet.
Not yet?
Not yet. Now we do.
Okay, cool. So this right here is a Rosette Nebula. And when we're looking at the Rosette Nebula, we're looking at a star-forming nebulae that has largely completed most of its star formation activities. The open star cluster has emerged from it, which is all these stars in the center here. And there's still enough ultraviolet radiation coming off of this open star cluster to continue to ionize the hydrogen gas cloud, which has now really started to disperse. There are regions in here where we suspect there may be some star formation still occurring, specifically in these areas here where you got some of these dark wisps, because you definitely have some cold hydrogen sitting around in here, which shows that there could be some further collapse happening. But largely, this is what the Orion Nebula will look like in probably another 10 million years. Now, the Rosette Nebula is naked eye visible from Frosty Drew on nights like tonight, but it is extremely dim, and most of what you're seeing is not so much the nebula, but it's more the open star cluster that has become visible. Now, this object is, strangely enough, was not seen by Charles Messier, which is kind of odd because we can see it naked eye right now. And I wonder if we've seen a decent amount of evolution in this object over the last couple centuries, because it is quite visible. And Charles Messier, he was looking for comets, and comets look like deep sky objects like nebulae and star clusters in the sky if you can see them, unless they get really bright like Comet Neowise did last year. So I'm surprised he overlooked this one. And when you think about it too, like Messier 1, the Crab Nebula, is super dim. And yet he saw that. So, and that changes over a period of 10 years because it is expanding very quickly.
So Scott, Gaming with Aiden just asked too. He said, "Are the pictures from your telescope? Are they from the main 16-inch telescope?" So I think he just wants you to know which telescope you're using.
Sure, I will show it to you real quick here. So let me just bring up my window here, and I'm going to stop presenting for a minute, and I'm going to see if I can pin my window real fast here. So is my window big for you guys or no?
Not yet.
All right, it might not get there, but we'll try anyway here. So I got my little nifty red light. So right here, this is the mount that I'm using tonight. This isn't the 16-inch telescope in the dome. This is one of our portable telescopes. So this is a research grade mount. And I have a 4-inch refractor telescope attached to it tonight. And then on the back of the refractor, I have the camera right here, which is hooked up to my laptop. And this is giving me a good wide field to shoot with, but it's only giving me 4 inches of aperture. If I was shooting this through the primary 16-inch telescope, then it would be, we wouldn't have this field of view that you see right here when I go back to the image. Instead, if we were shooting through the 16-inch, we would only be looking at this region right here. And that's because the 16-inch telescope has got substantially higher focal length. So the focal length of the telescope I'm using tonight is about just under 800 millimeters. The focal length of the telescope inside the dome, the 16-inch, is 4,000 millimeters. And so that's a big difference in what we can actually see here. Now, let's see what else we have out here in the sky. Because we have
a second.
What's that?
I've got the Whale Nebula. Or sorry,
let's switch over to Derek, and then I'll jump over to a Wolf-Rayet star.
Oh, there we go. That'll be fun. All right, so this one is a galaxy. It's kind of got some interesting things going on. So this is called the Whale Galaxy, and it's not a symmetrical galaxy anymore. It's been disrupted, but it still has dust lanes, and it still has it's an edge-on disrupted galaxy. But if you kind of look at it and you squint, you can kind of see that there might be a fin here, and then this galaxy up here might be the whale blowing a spout of water. But you can definitely tell that it's fatter on this end, and it kind of tapers off to this end where the tail would be. So you can kind of see maybe how astronomers would call this one a whale galaxy. This is located over here in the Coma Berenices constellation. It's actually in Canis Venatici, but that's just a line. So, but it's if you go kind of up here from that one, you've got that galaxy, and my solver window is sitting right on top of it, so that's super annoying. Let's see if we can get rid of that. So unlike Scott, I'm obviously not outside with my telescope. I have it set up to run remotely, which is nice in the winter because you don't have to freeze, but it does have its own set of challenges. So, the Whale Galaxy, kind of fun. And you can really see how much dimmer that is than the M65 and M66 that we looked at earlier tonight, where they really do jump out a little bit more than this one is. But this one is still visible in a fairly typical 8-inch Dobsonian.
The little bit that you were saying looks like a water spout there. Is that actually part of it, or is that a different object? That's
another background galaxy.
Okay.
And then below this image down here is another galaxy. You know, we can see that over here in the planetarium software. So we've got this disrupted galaxy. These two probably interacted, which caused the disruptions in both of these galaxies. And then this one is either a dwarf galaxy that's orbiting this galaxy or a background galaxy. I'd have to again look that up. I'm not a wealth of knowledge like Scott is, but I do have a lot of fun with this, so I try.
It's all that matters.
I wanted to note, Derek, that it's nice and warm where you are. So I'm sitting out here in exposure, and I forgot my jacket, so I'm just wearing my fleece, and I don't have any hat on because, you know, I'm a trained astronomer, right? This is
I'll have to
winter in New England.
I'll have to forward your being prepared email to you.
I know.
Right.
It is required to dress properly to visit.
Where's your jacket and hat? You had it.
There's somewhere around here. I'm not sure exactly where. So I have a wolf raid if you guys want to see it.
Yes, definitely.
All right. So this is an object called NGC 2359. And the object that we're looking at is in the center of the field here is called a Wolf-Rayet star. Now, a Wolf-Rayet star is a rather interesting object. It's not like a white dwarf that we were talking about earlier. It's also not like a supernova. It's its own little thing happening. And to understand what you're looking at, you have to understand a little bit about how stars interact with the immediate space around them. So let's take the sun as an example. So the sun has this really amazing kind of balloon or bubble around it called the heliosphere. And everything in the solar system, or at least the inner solar system, is inside the heliosphere. Now, the heliosphere is a product of the sun's intense magnetic field and mostly a substantial amount of plasma or charged particles that flow outward from the sun. It's the sun's energy. And we call this the solar wind, and every other star we would call it a stellar wind. Now, the stellar winds of a star move at a specific rate, but it's not static. It's not the same. Changes in the star's evolution can change the speed of the star's stellar winds. As in the case of a Wolf-Rayet star like this, what's happening is you have a very high mass star, a star that is a supernova candidate. It had a very constant stellar wind that was moving slower through its more stable periods of its life. But then as the star dropped into its red giant stage, it exhibited an intense amount of radiation and energy expulsion as it triggered into the fusion of heavier elements. And it cast it, and the stellar winds that left the star during that stage left at a substantially faster rate. They're charged particles, and the charged particles in the stellar wind at that point are slightly different than they were in the old stellar winds. And those new, faster-moving, energized stellar winds catch up to the old stellar winds and ionize them. And that ionization effect of the new, fast-moving stellar wind bombarding the old stellar winds is what you see in this envelope right here. The Wolf-Rayet itself is right outside of the field of this. It's actually this star over here is the Wolf-Rayet. And at this time, these are the stellar winds that it's catching up with over here. So Wolf-Rayet stars are not as common as a lot of other objects that we see in the galaxy, though we do see several Wolf-Rayet stars in the sky. One very well-known Wolf-Rayet star is called the Crescent Nebula in the constellation Cygnus, and sits right along the galactic plane. This sits right along the galactic plane as well. This is commonly referred to as Thor's helmet. Jess can probably attest to that since she's a big fan of the Avengers universe thing. I could do without it. But this is on the galactic plane that we see in the wintertime, which is the Perseus arm of the galaxy. And when we look at the Perseus arm, we're looking away from the galactic nucleus that we see in the summer. And that's kind of, you can tell, like over the night, as we're looking at different regions between Derek and myself, that some fields have a lot of stars in them. And then some fields have a ridiculous amount of stars in them, like this. And that's an indicator of, are we looking on the galactic plane? Or are we looking off the galactic plane? Because you're always going to see more stars on the galactic plane. I mean, a subtle little fun fact is that if you look into the galactic plane towards the galactic nucleus and then beyond and try to look at space on the other side of the galaxy, outside of the galaxy that's in line with the galactic plane, you can't see it. Because eventually, all the stars in the galaxy fill in the gaps. And that's impressive. That there are that many stars out there.
I think it wasn't until we discovered or invented, however you want to perceive that, radio astronomy, that we were able to look through the galactic core and see anything about the other side of the what's on the other side of the galactic core. It was kind of a mystery for a long time.
Oh, really?
So I'm taking a long picture of a spiral galaxy that's in the Virgo supercluster M100, and I just wanted to do a longer photograph. This one will be 2 minutes to really bring out some of the detail in that galaxy structure. It is a face-on grand spiral galaxy. It's not quite as big as M101, which in my telescope takes up the entire field of view. It's probably actually bigger than the field of view in its entirety. We've got about 40 seconds left on this picture, and 10 seconds to download or something. So I'll start sharing after that comes in, and we'll see several galaxies in this field of view. Because as Jess was kind of talking about earlier, if you look in if you look in any direction, you're just going to find galaxies. It's just galaxies forever. But the Virgo supercluster makes that true for close-in galaxies. So amateur astronomers can, basically get the same effect that you do with the Hubble Deep Field, using galaxies that are only 30 to 150 million light years away instead of, a billion light years away. All right, picture's downloading. So we'll go ahead and share entire screen. Let's go over there. All right, so you should be able to see the, so that's the planetarium view. And then this is what the telescope sees. So you can really see, this is M100 here. And then you can really see, you've got the spiral just comes out from the core and goes all the way around. And this one comes out from the core and goes all the way around. And there's no bar structure. So it is, a pure spiral galaxy, whereas the bar structure seems to occur after the galaxy has gone through a little bit of an interaction with some other galaxies, and the spiral arms have started to be disrupted. And I learned an interesting fact about our Milky Way galaxy, or at least the current leading theory. I won't say it's a fact, but the current leading theory is the Milky Way has 4 arms, 2 old arms and 2 arms that are younger, which I found kind of interesting in what's basically going on there, as the theory says, or the theory goes. The older arms are basically, there's no star formation going on. But in the younger arms, you've got all the star formation going on. So they're kind of the active parts of the galaxy. So I'm actually, doing some reading to try and read up on that and see if we can figure out a way, or see how that was figured out and kind of the data sources on that, because we obviously can't send out a probe and take a picture back on the Milky Way. That would take a long time. Like billions.
Oh boy, Derek, we just got a question specifically for you, and it said, ask Derek if he is a multi-universe or single universe believer.
So I don't know. That's a good question.
This is from Ken.
Yeah, I see it. I just pulled up the window. I see it. So for me, it's, you have to define universe. So I'm not really up on what the definition of a universe is. So we at one time thought the galaxy was it. In the 1900s, we finally realized and had a lot of proof and widely held understanding that the galaxy was not it, and we had the universe. So now we're kind of getting into the era when, all right, we've got a universe. Do we have a universe or do we have multiple universes? I don't know. It's it's a big problem or a big question, and I would like to think there are multiple universes, just because it means there's more out there. If it's true or not, I don't know. Does that work for you, Ken?
Well, that's the answer. That's it.
My answer. But yeah, even so, you got this smudge here. Oh, cool! It highlights in this view. That's really cool. And then you've got these are background galaxies. There's another background galaxy over here, and then it's just crazy how many galaxies are really in this field of view. And if we go over here to the planetarium, it kind of gives us, these are the major ones because they're the ones that are highlighted with the actual catalog items, but there's more around here. And if we zoom out, you get an idea for what the Virgo supercluster is all about. You got galaxies all over the place. Oh man, follow-up question. One Big Bang or multiple Big Bangs? I don't know. Never thought about it.
Ken's asking the deep questions tonight.
Yes, apparently.
Ken, you'll have to let Derek think about that for a week and get back to you next week on that one.
That's going to take at least a week of pondering. So where was Scott was going for something, wasn't he? Did he get lost again? Let's see.
There he is. He's back.
I'm here. I got Messier 51 if you guys want to see it.
Yes, that's a good one.
All right.
You and your no trees to the northeast.
Yeah, you look treed in over there?
Oh, yeah. My observatory is built against a tree line.
I noticed that you lost a tree in the last windstorm.
Yes, unfortunately, that one wasn't anywhere near the observatory.
Oh, yeah, of course, right?
Yeah, it fell across the driveway, That would be the usual tree to fall.
All right, you guys got it?
Yeah.
Yes,
okay.
Nice.
So, in this view here, now again, I'm using a very wide-angle telescope, so the galaxies are going to appear a little small. But in this case here, we're looking at two galaxies that are interacting with each other. We're looking at one is a very well-formed spiral galaxy, which is the galaxy on the bottom. And then we're looking at another rather distorted galaxy right above it. And the reason why it's distorted, you see these little lines right here, is because someone just bonked the telescope. The reason why it's distorted is because you have this galaxy is kind of taking this smaller one apart, and they will merge. They will become part of the same galaxy when this is completed. In this case, the larger galaxy. Now, the designation of this galaxy is Messier 51, and it's often referred to as the Whirlpool Galaxy, or the Whirlpool Galaxy. Now, Messier 51 is a really great target because a few years ago, we actually observed a really fantastic supernova that occurred in this galaxy. And it's not uncommon for supernovae to occur in this galaxy. We actually see it happen quite frequently. Now, you won't totally notice it at this focal length because we're just a little bit too zoomed out. But when the big telescope inside, you can often see them with just your naked eye. Now, I just moved the telescope to another object. I think Derek might have showed part of it earlier. It's called Messier 101, which is commonly referred to as the Pinwheel Galaxy.
Yeah, I just talked about that one. I didn't actually show it.
Oh, nice. Well, let's see if let's see how the image comes out. I'm doing it. It's collecting right now. We got 30-second exposure running, so
Yeah,
let's see where we're at.
I did just
And
have M100 up, which is a similar structure but smaller angular size.
so you got it here a little. It's a little bit here. It's a little bit washed out. So we're still in a part of the sky where we're going to see it a little bit washed out. But here you can see all the spirals of this galaxy. You got a little smaller galaxy down here. And this is, so when you're looking at the sky, you have the Big Dipper and the handle of the Big Dipper, and the star at the end of the handle is called Alkaid. The star Alkaid sits right in between Messier 51, which we looked at just a moment ago, and Messier 101, which is this object. They're kind of right across that area from each other. And this is kind of on the very edge of the Virgo supercluster. So you see some of the Virgo supercluster galaxies. Now, this one here, I don't know if we're going to get a better exposure on it because it is still in some of the light pollution. But I am going to swing the telescope over to a region of the Virgo supercluster called Markarian's Chain. And Markarian's Chain is a region of the supercluster that has dozens of galaxies in the field of view. So let's see if we can move it over there real quick.
How many arms does that the pinwheel have?
So I don't know offhand, but it is what's considered a grand spiral galaxy. So it has several arms.
If you want to let me show something while you're lining up on Markarian's chain. We might be able to have a slightly better view of the last two that we looked at. So I don't have these live. These are pictures that I've taken in the past, but we'll do a quick share for that.
Oh,
so
that's
a single image of M51 using my telescope. So longer focal length, so we have a closer view. And you can really see what Scott was talking about there, where you have material being transferred from this galaxy remnant onto M51, and the arms of M51 really do just look like that whirlpool as it's pulling that material, quote unquote, off of that galaxy remnant. And it's pretty cool, two very distinct spiral arms. If we go over to M101, which this one is, that grand spiral galaxy, and you can really see some of the, there's some dust lanes in here, and you've got, more active regions that are brighter in some of the, fringes of the arms. And these arms, they go quite a bit further out. That they just aren't apparent in the single exposure. But to answer the question on how many arms, it's interesting because if you follow this one, it looks like it splits right here, and it goes that way, and then also goes that way. And then if you follow this one, it kind of merges with that one, and then gets over here, and then there's something going on over here. So somewhere between 2 and quote unquote 3. I don't know if science has an answer for that one, but just if we look at it visually, it's not quite as distinct as the M51 are spirals, but nonetheless pretty structured grand spiral with no bar in the middle. So all right, if you've got that lined up, Scott, I'll stop presenting.
I do. I'm just doing some quick tweaks to it so you can get a better view. I'm going to lower my ISO a little bit because I feel like it might be a little bit too high for this, but I'm going to share this right now while I'm doing the next capture. All right. So this is actually quite a good view of Markarian's chain because it's more than just Markarian's chain that we're seeing here. We also have this galaxy right here, is this is what is this? Is Messier 8078? I think it is. The galaxy that we took a picture of the black hole in with the Event Horizon telescope. And when you look around this image here, you're seeing galaxies everywhere. Like this is a galaxy, this is a galaxy. These are galaxies here. These are on-edge galaxies. These are what we call elliptical galaxies, very large galaxies. This here is a humongous galaxy. Elliptical galaxy. It's one of the biggest galaxies we know of. And then these are galaxies out here, and this is galaxies. These are galaxies. These are galaxies. They're everywhere. Like this image is just loaded. All these faint spots out here are galaxies. Now, this is part of what we call the Virgo supercluster. And this right here, this chain of galaxies that you see here, we call this Markarian's chain. And there's several Messier galaxies in here as well. And this is where I lowered my exposure a little bit, so it's not my exposure, my ISO, so you can see a little bit more of the galaxies. But my exposure time is just really short right now for an object like this. Now, these are the fields of view that I like to work on when I'm doing my own data collection, because with enough data, you can draw out galaxies in the background that you wouldn't normally see. And a couple weeks ago on the live stream, I showed an example of this, of one of the objects I'm working on right now, called the Coma Cluster. Now, if I tried to capture the Coma Cluster right now, using the same settings I've been working with tonight, someone got me my jacket, woo! Then you wouldn't even see any of the galaxies in it because it's just so dim. And it's so small comparably. In this field, you can see some of them. But normally I would be using exposures at a little bit lower ISO, so a little less noisy. And I would be going up to about 120 seconds, 2 minutes, to be able to capture a clean field of view. Now, Derek may have an image sitting around of Markarian's chain. I might have one too, actually, captured previously that we can show off. Let me take a look real quick on my system here, my drive, and see if we have it. Because Markarian's chain is really just such an amazing object to look at. We do look at it in the telescope here, and when we look at it in the big telescope, you get a pretty good view of pieces of it, though you can't see the entire galaxy or the entire chain altogether because it's too big. Let me see if I can find Markarian's chain real quick here, and then I'm going to get ready to. Yeah, I do have a picture of it, so I'm going to share this image here really fast. Give me 1 second.
Meanwhile, I just need to say, too, that seems like Ken's kind of throwing out some fighting words there, Derek.
I see that. Oh, he's still got
what's going on here?
Answer.
Ken is saying in the chat there that if Derek is holding on to one Big Bang, he probably still believes in a heliocentric universe, a true pre-Galileo person.
Is that Ken Vetter?
No, Ken Sebesta.
Oh, Ken Sebesta. All right, I'm going to switch my presentation real quick to an image that was actually, this is an image I worked on. I didn't actually do the capture, though, of this because I was working with, let me see a tab, my boss and colleague at Brown University. You seen the chain or no?
Seen a Wikipedia page.
Yeah, that's let me get my designations so I can get the telescope on it. Let me switch over real quick again to the right page here. A tab. I use my browser to show images because I could do it with a tab instead of having to do it with an application that likes to crash my laptop. So this here is Markarian's chain. This is an image that was processed, where we actually extract information that is not really visible in just the exposure itself. Now, this was captured by a person named Bob Horton, who's the astronomy labs manager at Brown University, and he sent it to me to be processed. And we did this as part of the Physics 270 lab. Now, this is a good example of what you could see in Markarian's chain, but this is not a lot of data. This is only 5 sub-images that went into this. So you're talking about 10 minutes of exposure. If we really wanted to work on this, we would try to capture, up to 20 hours of exposure. And then we'd be able to bring out significant detail in the chain. But in this image, you can tell that just with this 10 minutes worth of data, that all of these stars that you see, stop minimizing, are roughly galaxies. I mean, there are galaxies everywhere here. All in the background out here, all down here. This is a galaxy. These 2 galaxies are interacting with each other, and it's causing this galaxy here to lose its shape and become very irregular. These will turn into a starburst galaxy. And these here are very large elliptical galaxies.
Yeah, that's such an awesome picture.
And this is, when you're looking at this, keep in mind that the telescope at the moment is looking at this object right now. And this here is the live view. Right here. And though this is a very dim view of it, and this was with a higher ISO right here, the orientation is different than the image we looked at before. This is about 90 degrees to the left of the image we were looking before, which had these 2 objects at the top, and then the swung out this way. And this is the region where you were able to see a lot of those background galaxies that are almost not even visible right here. But having 78 down here, this is notable because Messier 78 is just such a humongous elliptical galaxy. And this is the one where we actually took the picture of that black hole. So with all that said, I am going to be stepping off of the live stream right now. And Derek will wrap it up with you guys. So thank you for having me patch in tonight.
Yeah.
This is a real quick tidbit. This is a taste of things to come. We want to be doing live streams like this where Derek largely runs the live stream, and we have a representative from Frosty Drew on site patch in with a telescope, and then we kind of go back and forth with all the team members and astronomers that are on that are presenting. And we want to add this as an augmentation piece alongside our on-site events going forward. So you guys are early enough to catch us in the still of our testing phases, but we will perfect this and work the bugs out. So it was great seeing all you guys tonight, and I will talk to you later. And then Derek, it is all yours.
Yeah, thank you. That was great.
Thanks for joining. Okay, so I just brought up one image that I had of Markarian's chain from 2015, just to kind of wrap up with here. It's been great having all of you guys. With Scott on the line, we were able to go an extra hour, so I appreciate all of you that stuck with us. I was planning on doing about an hour, but Scott being there, he always adds his level of detail and can bring it to the next level. I think pretty typically we're going to try for an hour on these Friday sessions, and I think the plan is to do these rain or shine, and hopefully we'll have more shine than rain, but it is New England, so yes, fingers crossed. So I think with that said, thank you for joining us tonight, and we'll plan on doing this again in a week. Thanks everybody for tuning in.
Bye.
Bye.